You may remember that we ended the previous video with this function. We did not continue anymore because it was getting long. So today we are going to see what we can say about this function. We want to see how its graph looks. You can already see that, but let's come to that systematically. First of all, as we already noted earlier, this is a rational function because it's the quotient of these two polynomials 1 and x. The numerator polynomial 1 is in fact the constant function 1 and the denominator polynomial x is the identity function of R. And both of these 1 and x have their domain equal to R, the set of real numbers. However, we cannot choose R to be the domain of this because of the problem of division by 0, which is not allowed. And that is why we have to remove 0 from R. Now, of course, if you want, you can choose some other domain here. This is the largest possible domain that one can choose, from which this problematic point 0 has been removed. Any other real number, any non-zero real number you can put in place of x and you can get a reciprocal 1 over x for that x. But you can choose some other domain as well. For example, you can choose the set of all positive real numbers, which is this interval, to be the domain of this function. Technically speaking, that will be another function, although the rule is the same, but the domains are different. But again, what we have to keep in mind is that the denominator polynomial may be 0 at some points. Those points have to be removed from the set. There should not be elements in the set which you want to take as the domain of your function, your rational function. Alright, now with this domain, this one can go for drawing the graph of this function in the usual way. One first of all looks at some function values, then plots them and then joins them, the usual stuff. The text shows this table where some negative values have been chosen, some positive values of x have been chosen, and the corresponding function values have been recorded. And again, there you won't get any 0 here because 0 has no reciprocal. It lies outside the domain of this function. Now, if one plots these points and then does the usual thing, one will get a graph which roughly looks like that. I say roughly because in drawing this I have not been really accurate. I have just tried to show the general shape of the graph. And this graph is in two parts. It's broken at x equal to 0. At x equal to 0, of course, there is no y value. F of 0 is undefined. So, when x is 0, there is no y value. So, the graph means both of its parts will not touch the y-axis. Elsewhere, there are values. And the graph looks like this. You can just, instead of looking at these values, you can simply think of what this function does. Say you take a very large positive value of x. Say x equal to 1000. Then f of x is 1 over 1000. That is a small value. And the larger x becomes, the smaller 1 over x becomes. And that is why as you go further and further away from the origin towards the positive side, the y value becomes smaller and smaller, and that's why the graph is going down. On the other hand, if you come closer and closer to the origin from the positive side, the reciprocal there, that means now x is decreasing in size because we are getting closer and closer to 0. Now x is positive all the time, so 1 over x is also positive, but now x is decreasing, 1 over x is increasing, and that's why the graph goes like this. and the closer you come to 0, the higher this value becomes. And an exactly similar thing happens on the negative side as well, but now with negative signs. For example, now if your x goes away from the origin, from this x equal to 0, x is negative all the time, but 1 over x decreases in size. If you ignore the negative sign, x is increasing in size, ignoring the negative sign. 1 over x is also negative. If you ignore the negative sign, here also it's decreasing. So as you go away from the origin, the y value will be smaller and smaller and smaller. So the graph goes up. All the points in this part of the graph have to lie below the x-axis because y is negative. X is negative, 1 over x is also negative. But in spite of that, that kind of behavior is seen here also. Similarly, as you come closer and closer to 0 from the negative side, the magnitude of 1 over x increases, but with a minus sign. And that's why this becomes large but negatively large. And that's why roughly the graph looks like this. The next one is the modulus function or the absolute value function. Let us first see the function and then we will draw its graph too. For any real number x, we define the modulus or the absolute value of x by the following rule. The modulus of x or the absolute value of x is denoted by this symbol. Enclose x within two vertical bars. And the definition of it is this. By definition, this is equal to x itself if x is non-negative. That means if x is either 0 or positive. In that case, the meaning of this symbol is simply x. On the other hand, if x is negative, then this means minus x. This quantity is called the absolute value of x or the modulus of x. Now the function f from r into r given by or defined by f of x equal to mod x is called the modulus function or absolute value function. But again, never forget to check that whatever you have defined is a real legitimate function. In other words, a well-defined function, or put simply, is actually a function and not just a general relation. For that, what do we have to do? You have to show that every point in the domain has a unique image in the codomain. That's what you have to show. In other words, you choose any input from the domain. That input first of all should have an output in the codomain. And the second thing is that that output should be unique. One input should not have more than one output. Is that the case here? Say I take any x in R, that means x is a real number. Exactly one of these two things will happen. Either x is greater than or equal to 0 or x is less than 0. If x is greater than or equal to 0, then the output is x, which of course is a unique real number. I mean, for that type of x, we are getting x as an output and nothing else. Similarly, if x is negative, then the output is minus x, which is again a unique real number. And that is why this is indeed a legitimate function. Actually, here itself we have defined the function, but we are giving it a name, a letter, say f. This itself is the absolute value function. Next comes the graph of this function. For the graph again, let's just first make a table of sum of its values. This graph is easy. Easy means easier than the graph of 1 over x. Graphs of rational functions are really, they are not that simple and varied. It depends on what the function actually is. Okay, so this is my x and this is absolute value of x. Say I choose minus 1, say. Right. Now, what is minus 1? Minus 1 is a real number. Is it positive or negative? Negative. That means this condition is satisfied. So, the absolute value of minus 1 should be minus of the input. That means minus of minus 1, which is 1. Say I take 0. Then I am in this region of the definition. So, when x is 0, the output should be x itself. That means 0. If I take 1 here, the output will be 1 because again I am here. My input is now positive. And of course, again, it's not necessary to only take integers as input. We can take rational numbers, general rational numbers, irrational numbers, anything. So let me just take, say, square root of 2. It's also positive. So the output is also the input itself. And let me just take 2, just to fill the table completely. So again I have to, now if we plot these points, what shall we get? So this is our x-axis, y-axis. Let me also roughly mark out the points. Say 0, minus 1, although we won't need minus 2, but let me simply write. Okay, so when x is minus 1, say, here also on the y-axis this is 1. When x is minus 1, the output is 1. That means minus 1 comma 1 is a point on the graph. When x is 0, the absolute value function gives us 0. When x is 1, we again get 1. When x is root 2, of course, I am not going to locate it here. It will be somewhere between 1 and 2, you already know. When x is 2, y is 2. So, if one really calculates a lot of these point pairs, one will realize that joining them one gets two straight lines like this. Okay, straight lines means they end here, they are not extended like that. On that side they are extended indefinitely. So this is the graph. You can already see that in locating this 1 and minus 1 I have made a mistake. Mistake is that it seems like 1 is closer to 0 than minus 1 is to 0. So that's just a drawing mistake. You should understand that if you do it correctly, using a ruler and everything, then this line and this line both will be making 45-degree angle with the x-axis. So that is the graph. It looks like this. It's this V-shaped graph. That's the graph of the absolute value function. Next, there is one more function that you will encounter here and there in many places. That's the Signum function. Note that unlike a rational function whose domain needs to be chosen carefully so that we don't end up dividing by 0, for the absolute value function the domain is the entire set of real numbers. There is no problem. The Signum function, it has been given the name SGN, is a function from the set of real numbers into the set of real numbers is defined as, just like the absolute value function, this is also partly defined or defined in a piecewise manner. At in different parts of the domain, the function definition is different. By this formula, SGN of x is defined to be equal to 1 if the input x is positive, not like the absolute value function, not non-negative, actually strictly positive, is defined to be equal to 0 if x is equal to 0, and is defined to be equal to minus 1 if x is negative. So although it looks somewhat like the absolute value function, but the definition shows that nothing much really changes as x changes. In these parts, the function keeps some constant values. In particular, it takes on only the values -1, 0 and 1. We do not get any other output. But for the absolute value function, you get many outputs. In fact, you actually get all the non-negative real numbers as outputs. So let's now see what its graph will be. In this case, there is in fact no real need to even make a table. Just from this, we can straight away draw the graph. So let's do that. For the absolute value function, we really did not need the region that lies below the x-axis. Here, however, we will need because there is a negative output. Okay. Now there is something that we have to note carefully here. Let me first mark out these points -1 and 1 on the y-axis because they are outputs. This is -1, it's here actually, and this is 1. Okay, now if my input x is positive, what is the output? Let me just show you the process. The output is 1, right? That means the output is here. This is 1 point on the graph. If my input is something else, but again positive, the output is still 1. So it's constantly 1 if the input is positive, it does not change. That means if you join all these points, you should then get this straight line that is parallel to the x-axis and at a height 1 unit from the x-axis. But what about the point 0? If my input is 0, then the output is also 0. That means this single point, which we also call the origin, is also a point on the graph. Note carefully that this line is not allowed to touch the y-axis. Why? Because if it touches the y-axis, that will mean that this point whose coordinates are 0, 1 should be a point on the graph. But at 0, the function does not have value 1, its value is 0. Now, how do you show geometrically on paper that this line should not touch the y-axis? This is how. What we do, we draw a small circle around that point. That circle prevents this line from ever coming so close to the y-axis that it touches the y-axis. And we keep the circle white to indicate that the line stops there. Well, actually it does not stop there, because if I really geometrically draw a circle with some positive radius, this is a circle with some positive radius, right? No matter how small that radius is. It's just a representation of the fact that this should not touch the y-axis. Okay, just that. Nothing more than that. Similarly, on the negative side of the x-axis, all the values are constantly -1. So on this side, you will similarly get this parallel line, parallel to the x-axis again, but this time 1 unit below the x-axis. This line also, because of a similar reason like that, should not touch the y-axis, because when our input is 0, the output is not -1, it is 0. That's why here also a white circle is drawn to indicate that that line also is not allowed to touch the y-axis. To further emphasize the fact that this is a point on the graph, we draw a black circle here. So this is the graph of our Signum function. It has three parts. One part is this ray. I don't call it a straight line because it has an end. It's not indefinitely going on either side. It goes indefinitely on that side, but here it has an end. So this ray, another part is this ray, and another part is this single point. Okay, so that is the graph of the Signum function. And after the Signum function comes this very interesting function which is called the greatest integer function. Its graph will look like a staircase. And that's why this function is sometimes also called the step function, the floor function. These other names are also available for it. We will, however, call it the greatest integer function, because that name will help us remember what it is actually. The greatest integer function. It has something else with it as well, the least integer function, its partner. We don't, however, discuss that here in this text. For any real number x, we denote by this symbol x within square brackets the greatest integer less than or equal to x. First of all, this has to be understood properly. X is any real number. By this symbol, we mean the greatest integer less than or equal to x. It may be a little confusing at first, but let's see. Okay, let's take some values and see what their greatest integer values are. Sometimes we also say like this, that for a given real number x, this is the greatest integer value of x. It is best if we think of these things on the real line, geometrically. Then it will become very clear. Let me first take x equal to, say, 1. And let me draw the drawing here. Not the graph, that will come, but before that, for our help, we are going to draw simply the real line here. And on the real line, we locate these points. 1 here somewhere, we will have 2. Because we have uttered integer, you can imagine that this function or this symbol has something to do with integers Well, the definition is in front of you, but that's why we are drawing integers. What does it say? That what should this be? This should be the greatest integer less than or equal to 1. What are the integers? Let me denote by n an integer less than or equal to 1. What are the integers less than or equal to 1? You see 1 here. 1 of course is less than or equal to 1, and all the other integers that lie to the left of 1 on the real line, they are less than 1. That automatically means also less than or equal to 1. So, if you think of the set of all integers satisfying this inequality, these are the integers. Among them, what is the greatest? 1 itself. So, that means the greatest integer less than or equal to 1 is 1, and that is why this is 1. Similarly, if you think of the greatest integer less than or equal to 2, you should then get 2, because now 2 is also included. These integers all are less than or equal to 2, but 2 is also itself less than or equal to 2. So you get this. And repeating this process with every integer, in fact with 0 and even with negative integers, you come to the realization that for any integer n, its greatest integer value is n itself, right? But our x is not always integer, right? X can be fractional also. What will happen then? Say now I take a fraction. For x equal to say 3 divided by 2, which is the middle point of the line segment joining 1 and 2. 3 divided by 2 is 1.5. For this though, what are the integers less than or equal to 1.5? In this case, because 1.5 itself is not an integer, it will not come in the list of integers less than or equal to 1.5. They are these: 1, 0, minus 1, minus 2, all these things. All these integers are less than 1.5, less than or equal to 1.5, because that equality possibility is not possible here. Among them, the greatest is of course 1, and that is why this is 1. Okay, so on the real line, if we imagine everything, it becomes quite clear what the greatest integer value is. Geometrically, you do this. You locate the point, you look to the left of the point. The first integer that you encounter is the greatest integer less than or equal to that point. If the point itself is an integer, like in case of 1, then there itself you stop. That is the first integer you have encountered. You did not have to walk at all. Here if you have 1.5, you had to start walking, but then you got 1 and you stopped. That is my greatest integer, value of 1.5. Now if one starts to look at the decimal representation of an integer, for example, instead of 3/2, we have written 1.5. One may think that this 1 is the greatest integer value. that you just remove the fractional part, you keep the integer part, and that is your greatest integer value. This is a little problematic. It works well on the positive side. However, if you similarly look at the negative side, then things go wrong. If you think like that, say I have 1.5, I do not write 0.5, 1 is the greatest integer value. But now watch this. If I take minus 1.5, that means minus 3 over 2. What is this though? This is the middle point of minus 1 and minus 2 in this pictorial representation. If I erroneously, wrongly have formulated such a rule that disregard 0.5 and 1 is the value, then I should disregard 0.5 here and minus 1 should be my value, but that clearly is not true, because if this is your point and you start walking from it towards the left side, what is the first integer you encountered? Minus 2, not minus 1. Okay. All the integers less than or equal to minus 1.5 are minus 2, minus 3, minus 4 and so on. Among them the greatest is minus 2. So this value is minus 2. The rule is simple. You locate the point and look to its left. The first integer you encounter is the greatest integer value. Okay. And in fact, if you even take some irrational number, for x equal to say pi, what should this be? If you extend it on that side, I do not have much space to show everything, but if you just imagine that you have 3 here, you have 4 here, you know that pi lies between 3 and 4. 3.141592653, something like that, no? So pi lies between 3 and 4, not the midpoint, but it is in that region. So if we start at pi and start walking towards the left, the greatest integer less than or equal to pi is 3. So this is 3. Okay, with this understanding of the greatest integer value of a given real number, we next define this. The greatest integer function, it's also defined on the entire real line and has the codomain also R. Is defined as or defined by f of x equal to this. There are other symbols. There is another symbol to denote this, which is in fact the more commonly used one. This. We do not complete the square brackets. Okay, we keep the top open like this. That other partner of this function, which is the least integer function. If you think a little, you can yourself say what it is. That is denoted by this symbol. But since we are not going to discuss least integer function, so we settle for this notation. Okay, now comes the task of drawing the graph. This is interesting and a little bit complicated. It's not exactly complicated, but you can make mistakes if you are not careful. To keep things simple, I will not take too many x values. I will just take, say this is my 1, this is 2. On this side I take, say, -1 and -2, and we of course have 0 here. Now what I do, first of all, I draw vertical lines through the integers, dashed lines, okay. Why? That will become clear soon. Let me do the calculations on that side. The function is not exactly simple, but how do you figure out what the graph will look like? Let me do one thing. Let me first consider this type of input. Let x belong to the half open interval 0, 1. Again, why do I suddenly take this? That will also become clear. That means x is greater than or equal to 0 and less than 1. X is not allowed to be 1, but x can be 0. See, in the beginning itself, we can see that when x is 0, then the greatest integer value is 0. For any integer, the output is that integer itself. That means 0, 0 is a point on the graph. So now I can consider this situation. If I have already considered 0 and x lies here, so now I can consider, and this case is gone, x is greater than 0 and x already is less than 1. In this situation, x will lie here somewhere. And again, if you start walking towards left, what is the first integer that you encountered? Obviously 0. Before 0, you cannot encounter anything else. Why? Because the next integer lies on the right side, not the left side. These inequalities make sure that that is the case. And that is why for all of these types of x, I can at once say that the greatest integer value is 0, no matter what actually x is. For all such x, the greatest integer value is 0, which means that if my x is coming from here, y is always 0. So the graph should be the x-axis itself, at least in this part. So I make it a little bold. It's getting messy, but you can understand what I mean. However, the moment I hit 1, when x becomes 1, the greatest integer value is what? 1. not 0. So this line segment is not allowed to touch this dashed line. So just like that Signum function graph, here I draw one white circle to indicate that fact that this part of the graph doesn't touch that line. It however does touch the y-axis. So this left circle is black, right circle is white. Here of course I have gone past this 1. Now if you repeat this procedure with this interval, exactly the same thing, similar thing should happen. When x is 1, we have already seen that the value is 1 now. Say I have 1 here, so now the value is 1. This is black. So whatever segment of the graph lies here, that touches this line, but this lower segment does not touch this line. Now if x strictly lies between 1 and 2, that means x lies here, then what is the greatest integer value of x? You start walking towards left from x, the first integer you encounter is 1. So for all such x, the value is constantly 1. So again another line segment goes like this. However, it cannot touch that line, because when x is 2, the greatest integer value is 2, not 1. And that's why there is the white circle here. If you do the same thing with this interval -1, 0. At 0, of course, the value is already 0. But when x satisfies inequalities like this, then x lies here somewhere. And our leftward journey from x lands at us at -1. That's the first integer destination. And that is why for all such x, this is -1. So if my -1 is here, then this should be the graph in this portion. When x is -1, the value is also -1. When x is 0, the value is not -1. That's why this circle is white. So do you see the pattern that is emerging from this? It's like a staircase. That's why it's sometimes called the step function. And if you similarly continue here in this region, because we have it here, so let me just draw this part as well. So this is -2. Then in this part, the graph is again such a line segment. And it continues indefinitely on that side and on this side as well. So this is the graph of the greatest integer function or step function. After this we have one small thing, algebra of functions. That however I won't do today, because there are some things about algebra of functions that I want to discuss, which is not there in this text, but which will be useful in future. So let's do that another day. Another day means this Thursday. And that's just it for tonight. Tomorrow, what do we have tomorrow? Tomorrow we have Galva theory. I think we have already completed one section. Did we complete one section? No, we did not complete one section. There is, we still have some things to do. Okay, so tomorrow we will do that. So that's it for tonight. Until then, this is me, Lucifer, from A Mathematical Tool. Have a nice day.